morning, everybody. I'm Dr. Sreedevi, Assistant Professor, IARE College, Hyderabad. Today we are going to third session of Graph Theory Review of Basics. Today we are going to discuss some topics like a spanning tree of a graph, minimal spanning tree, then its applications, and some algorithms to find the minimal spanning tree of a given graph G. We have already seen what is the definition of a tree. When we are given a graph, connected graph with n vertices, and if G is circuitless, that is, we are given a connected circuitless graph and with n minus 1 edges, then G is termed to be a tree. Now we will see what is a spanning tree. So far we have discussed trees as a graph occurring as its own. Now we are going to consider a tree as a subgraph of a given graph G. We know that if we have already seen what is a subgraph of a graph. Yeah, subgraph means H is said to be a subgraph of a given graph G if the edges and vertices of H to belong to the edges and vertices of given graph G. And if if G has E edges, then that we can find 2 raised to E distinct possible combinations of the edges of G. So obviously, some of these subgraphs may be trees. A tree is said to be a spanning tree of a connected graph G if T contains all the vertices of given graph G. So for a graph to be a subgraph, do it requires every vertices to be in that subgraph? No. Because even if we are considering this graph, so this portion, this itself is a subgraph of the given graph G. Right? Now we are going to see what is a spanning subgraph. A tree is said to be a spanning subgraph we have seen if it contains all the vertices of the given graph. And a spanning tree is a tree which contains all the vertices of given graph. That is that we have how many vertices we have in this graph? We have 1, 2, 3, 4, 5, 6, 7. 7 vertices we have. And this tree from this subgraph should contain 7 vertices. That is, if I am having this vertex. These are the 7 vertices. And then I should draw a tree which contains all these 7 vertices. That tree is termed to be a spanning tree of the given graph G. These lines with this, see these lines, unbroken lines. I am connecting a tree with this vertex. If it is A, B, C, D, E, F and G, these unbroken lines connecting A to C, C to B, B to F, F to G, F to D, and D to E. It is a connected graph and contains all the vertices of the given graph. So it is a spanning tree of the given graph. That is the that have been marked on unbroken lines. Is the spanning tree of the given graph G. Okay. Now look at this graph G. How many vertices this G has? G has 5 vertices. So according to our definition of tree, how many vertices, edges it should have? It should have 4 edges, right? 5 vertices and 4 edges. So I have marked all these 5 vertices. And here I am connecting these vertices through edges like this. This is one spanning tree representation of the given graph G. And this is second representation. Okay? A graph may have different number of spanning trees. Since the vertices of our graph looks like just barely hanging together in a spanning tree, it looks like the skeleton of the given graph, right? Here also, it looks like the first tree 1. It looks like the skeleton of the given graph. Also, T2 is also more or less a skeleton of the given graph G. So it is sometimes called the skeleton or scaffolding of graph G. Okay. Since the spanning tree is the largest among all the trees in a graph, it is also called a maximal tree subgraph or maximal tree of a graph G. So, we know what is tree now. Now, what is spanning tree? Spanning tree is a tree that contains all the vertices of a given graph. And since it is the biggest of all the trees. Why? Because it contains all the vertices. Spanning tree contains all the vertices of given graph G. It is also called the maximal tree subgraph or maximal tree of a graph G. Spanning tree is defined mainly for connected graph. Why? In our definition of a tree is a connected graph with n vertices and n minus 1 edges, right? Since tree is always, so spanning tree is defined only for connected graph. Since tree is always connected and disconnected graph of order n, can we find any simple subgraph with vertices n? No. However, each component of this disconnected graph has a spanning tree, and hence it forms a disconnected graph with k components. However, each component of a disconnected graph has a spanning tree, and hence a disconnected graph with k components has a spanning forest consisting of k spanning trees. What is this forest? I hope you remember. Forest is a collection of trees. So when a graph is disconnected, it has disconnected into k components. We can have spanning trees of each of these components, and these spanning trees forms a forest with k components. So how to find a spanning tree of a given graph? We know what is tree, and now what is spanning tree, and now we are going to find the spanning tree of a given graph. If G has no circuit, then G itself is a tree, and we know that it's on spanning tree. Okay. If G has circuit, then delete an edge from the circuit. The resultant graph will be connected. Is it so? Yeah. Because when we are removing a circuit from a graph, when we are removing an edge from a circuit, the graph won't get disconnected. If G has more circuits, repeat the process and step 2 till an edge from every circuit is removed. That is, till an edge from last circuit is deleted, and leaving a connected graph, which is circuit free, containing all the vertices of G. That is, every graph has at least one spanning tree. When we were considering this, we have given two cases of graphs with 5 vertices. 2 spanning trees of graph with 5 vertices. We can draw different spanning trees from this graph also. Suppose here I am going this 5. I can put like this also. This is also a spanning tree of the given graph. Okay. So a graph will contain at least one spanning tree of that. We can find at least one spanning tree of a given graph. That is, the main result is every graph has at least one spanning tree. Okay. Now we are going to the concepts of branch and chord of a tree. An edge in a spanning tree is called the branch of tree. Here we have marked these bolded edges, and this constitutes the branches of this tree. That is, B1, B2, B3, B4, B5 and B6 forms the branch of this tree, whereas the edges that are not a part of this spanning tree are termed to be the chord. That is, C1, C2, C3, C4, C5, C6, C7, C8 are the chords of this spanning tree. Okay. Branches means the edge that belongs to the given tree, and chords means the edges that does not belong to the given tree. Main thing that we have to take in mind is that the edges and branches are defined with respect to particular trees. Consider this graph G with edges A, B, C, D, E, F, G, H, and we are considering this spanning tree of this. Here the edges are A, B, C, and E. Okay, so the branches are A, B, C, E. Other things D, F, G, H are chords with respect to this spanning tree T1. Whereas in this T2, see what happens? The chords of this T1 here have changed to branches. Whereas the branches of this T1 has changed as chords with respect to this T2. So whenever we are saying about branches and chords of a spanning tree, we are telling with respect to the given spanning tree. It is not, we cannot say in general. Now we can have another result. With respect to any of the spanning trees of a connected graph, G of order P and size Q, there are P minus 1 tree branches and Q minus P minus 1 chords. What is this order and size of graph? I hope you remember it is order means order is number of vertices and size means number of edges of a graph. Order and size of a graph. So order means if it has order P, that is number of vertices, that means here we call n equal to Q. Okay. We have used for this n, n is equal to P. Because we have been, while defining trees, we were using that if G is of order n and size n minus 1, then we used to call it as a tree. That is why I am saying that n equal to P here. And that is when, so order P and size Q. So what is the number of tree branches? Then it should be n minus 1, that is equal to P minus 1. And size means, and chords means the branches which are, edges which are not the branches of the given tree. That is Q minus P minus 1. That is equal to Q minus P plus 1. So there are Q minus P plus 1 chords in the spanning tree of a given graph G of order P and size Q. Now we will see some applications. In an electrical network, mainly we are using these things in electrical networking. With respect to any of its spanning tree in a connected graph G of order P and size Q, it has P minus 1 tree branches and Q minus P minus 1 chords. We know that if a given graph is a tree, if it has P minus 1 edges, that is the number of branches must be P minus 1. And how many chords we can find? Remember from the definition of branches and chords that branches are those edges which belong to the given spanning tree, and chords are those edges which are not the branches of the given spanning tree. So since there are P minus 1 tree branches, we should have Q minus P minus 1 chords. That is Q minus P plus 1 chords are there in a given graph G with P vertices and Q edges. Okay. Now we are going to the application of spanning trees. Spanning trees are mainly used in networking and all. So, consider this on a particular case. In an electrical network with n cords, that means n application of spanning trees. In an electrical network with n nodes, that means n vertices, and e elements edges, what is the minimum number of elements to be removed to eliminate all the circuits in the network? That means what are the minimum number of elements, that are minimum number of edges that has to be removed to eliminate all the circuits. That means we are required to find the number of branches as well as the chords. Here we have to find the number of elements that have to be removed. Means we have to find the number of chords. So number of chords we have as like that. It is, what is that? E minus n plus 1. Because earlier we have seen that if P is the order and Q is the size, then the number of chords is given by what? Q minus P plus 1. Right? That is here also. Here the Q is E and P is N. That is E minus N plus 1. Okay? It is the number of chords. Now we are going to second example. Consider we have a farm with 6 plots of land and these plots are full of water. How many walls we will have to be broken to? It will have to be broken to drain out water. Suppose the field is like this. Okay, we have 6 plots. 1, 2, 3, 4, 5 and 6. And this plot has how many vertices? It has 10 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay, here it is 8. 8, 9 and 10. 10 vertices. And how many edges we have? We have 15 edges. I have marked it from E1 to E15. So number of edges, number of walls that has to be removed means here the case is number of edges that has to be removed. And edges that has to be removed means we have to find the chords, because we have to find, we are using this spanning tree concept here. And we have to find the number of chords that has to be removed. And number of chords. And that is chords means here it is what we have E minus N plus 1. And we have written like that, E minus N plus 1, which is equal to 15 minus 10 plus 1 equal to 6. That is we have to remove 6 edges out of this to find our, to satisfy our condition. And removing the arbitrarily 6 edges from that given graph, the resultant graph will be looking like this. And from here, our solution. See how many walls will have to be broken to drain out water. And this happens and we can drain out our water. Okay. And we are now moving to next important concept, minimal spanning tree. Let G be a graph with a positive real number associated with each edge E of G. Okay, then G is called a weighted graph. And each positive number associated with an edge E is called weight of the edge. Now we are going to the important concepts, minimal spanning tree. Before going to the introduction to minimal spanning tree, we will see what is a weighted graph. Okay, let G be a graph with a positive real number associated with an each edge E of G. Then G is called a weighted graph. And the positive number that is being assigned to each edge E is called the weight of edge E. And it is denoted by WT of E. Okay? Weighted graph. And what is the weight? That is, every edge is being assigned a positive real number. If every edge of a graph is being assigned a positive real number, then the graph is said to be a weighted graph, and the positive number real number that has been assigned to each edge. It is called the weight of that edge, and it is denoted by Wt of that E. If E is the edge that we are considering, and that weight is assigned to that, we suppose I have a graph like this. Here, this A, B, C and D, these vertices. If I am assigning a number like this, 3, 4, 2 and 1, and this AB is said to be of weight 3, BC is said to be of weight 4, AD is said to be of weight 1, whereas DC or CD is said to be of weight 2. Okay. Where we are applying this weighted graph in our real life situation. Suppose we are given different cities of a country, and each cities will be connected through air. That is, the cities may be air connected. The cities may be certain kilometers apart, and which are positive. These kilometers, we know it is obviously a positive real number, and therefore the graph with a weighted graph, we can find a weighted graph connecting these cities, and the weight of the edge is the distance between the cities. Okay, suppose we have Delhi, here Kolkata, here Hyderabad, then Chennai and Cochin, here Bangalore and here Mumbai. You know, all these cities are directly connected with flights, and if someone wants to travel from Hyderabad to any of all these cities, so how we'll be using this? Because sometimes every cities are connected, and we know the rate of this distance between them and the rate of the flight charges, everything. So we will have either this distance may be represented in this graph, or a flight fare may be represented in these things, and we will be finding some minimal trees and all. How we are going to that, we will see on this next slides. Okay. Now we are going to the definition of minimal spanning tree. First, we have seen what is a weighted graph and how these weights are being assigned and all. Now we are going to our particular portion, subject portion. Let T be a spanning tree of a weighted graph. Okay. You know what is a weighted graph? That is, every edge has been assigned a positive real number. Then every edge of T is also weighted. Why? Because T is a subgraph of the graph G itself. The sum of weights of all the edges of T is called the weight of T, and which is denoted by Wt. Okay. Consider all the spanning trees of a weighted connected graph, and find the weights of all these spanning trees. A spanning tree whose weight is the least is called a minimal spanning tree. Okay, what is a minimal spanning tree? We have to consider all the spanning trees of a given weighted graph, and we have to find the weight of all these spanning trees. And the spanning tree whose weight is minimum is called the minimal spanning tree, or weight is the least quantity. The spanning tree whose weight is the least quantity is termed to be the minimal spanning tree. Now consider this graph. G, we have 4, 5, 6 vertices. So the minimal the spanning tree should have 5 edges. 1, 2, 3, 4, 5, every spanning trees. Because I have drawn 3 spanning trees of this graph G. And now what the same edge weights have been assigned to these spanning trees also. Now find the edge weight of this spanning tree, S1, S2 and S3. How much is the edge weight of this spanning tree? It is 10, 16, and here it is 13. Here it is 15. So which one has the minimum weight, least weight? It is this one. So it is called the minimal spanning tree of the given graph G. See here. The weight of these spanning trees are 16, 13 and respectively. Right here, it is 16 weight. Here it is 13 and here it is 15. Thus, the spanning tree S2 is the minimum spanning, turns out to be the with minimum weight. S2 turns out to be the spanning tree with minimum weight, and it is the minimal spanning tree of the given graph G. Okay. Now we have learned what is the spanning tree and what is minimal spanning tree. There are some algorithms to find the minimal spanning tree of a given graph. Of the main things are, there are so many algorithms. The main algorithms that we are using are Kruskal's algorithm and Prim's algorithm. Okay, we'll see how it works. Now we are taking to Kruskal's algorithm. Suppose here we have taken this, it's somewhat easy algorithm and we are doing it in 3 steps. The working principle is also so easy. Suppose we are given a connected graph G with n vertices. List all the edges of G in the order of non-decreasing weights. First, you have to list all the edges of G in the nature of non-decreasing weights. Starting with the smallest weight edge, sequentially add the edges, selecting one edge at a time, such that no cycle is formed. Process of step 2 is continued until all the n-1 edges are selected. These n-1 edges constitute the minimal spanning tree of the given graph G. The process 2 is sometimes referred to as greedy process. Now we will see how we are going to work with this Kruskal's algorithm to find the minimal spanning tree of a weighted graph. Suppose we are given a graph with these vertices A, B, C, D, E and Q. And it is a weighted graph. First we are writing what we were asked to do then. First we were asked to list the edges of G in the order of non-decreasing weights. That is, we have to put the edges of G in the order of increasing weights. That is, putting this, starting from the smallest, it is weight 5. Then this weight, this 5 has been put. Then this 7 has been put. Then this 8, then this 9, this 10, 11 and 12. So which is written like this. Now we are going to put this edge with weight 5. Then we are going to put edge with weight 7. Okay. Then first we have put edge with weight 5. Then then I put this edge with weight 7. Again then edge with weight 7. If I am adding that, it does not form a circuit, so I am adding that. Then came the edge with weight 8. Even if I am adding that edge also, then no circuit is formed. Next came the edge with weight 9. That it was going like that. But if it is being added, this will form a circuit. So that edge with weight 9 is being not added here. Then I had on edge with weight 10. If I am adding that, it can be like this also, which will make a circuit which is not permissible. So I just didn't add that. So I just added this edge with 10. Okay. Now I have added all these 5 edges. And this is the record minimal spanning tree. It can be also summarized in this tabular form. First we are given this graph with all the edges. So I am just marking the edges. Then the weights, corresponding weights have been put in it. Then whether to select this edge, yeah, we can put it. This CD can be put without any confusion. So this CD has been put here. Then whether it is possible to put that ED. Yeah, it is also possible. So I am putting that ED here. Then that QD is also possible. So QD. Then is that possible to put that BQ? Yeah, that is also being possible. So I am putting that BQ. Is it possible to put that BD? It's not possible. So then which one is possible? BA is possible. So I am putting that only. BA. Okay. This is the working principle of Kruskal's algorithm for finding the minimal spanning tree of a given graph G. Now we are going to the next algorithm, Prim's algorithm. Given a connected graph G with n vertices. First we have to name all the n vertices. Then we find an n by n table in which the weights of all the edges are shown. Entries in the table will be symmetric with respect to the diagonal, and now entries will appear on the diagonal. Indicate the weights of non-existing edges as infinity. That is, if we are given a graph with 5 vertices, one, 2, 3, 4, 5. We have to make a 5 by 5 table. And this, if we are given this edge weights, we have to enter this between 1 and 5. 1, 2, 3, 4, 5. Here also 1, 2, 3, 4, 5. One, 2, 3, 4, 5. Here between 1 and 1 there exists no edge and we will be putting this. 1 and 2 we will be having one edge, and if it is weight W1, I have to put the W1 here, and 2 and 1 also this W1 will be here. Okay, and like that we will be putting, and between here 5 and 3 there is no edge, we will be putting infinity in that column. 5, 3 position we will be putting infinity. Start from a vertex Vi and connect it to the nearest neighbor in the Vith row. Okay, say it be Vk. And construct the edge Vi Vk. And connect it to the nearest neighbor, that is to a vertex other than Vi and Vk that has smallest weights in the entries of Vi and Vk rows. Let it be Vm. Start from this vertex. Next step we have to, that is, if we are having first start from a vertex Vi, then go through all the entries in this row Vi, find the least entry, and this Vi should be connected to that. Let it be Vk. Just draw an edge Vi Vk. Okay, then now we have to Vi row and Vk row. Go through all the entries and find the least weight, least entry with least weight, and connect that vertex to this Vi or Vk according as which is the least weight, and then connect that to Vm. If the least weight quantity is Vm, then connect to that Vm. And continue, start from Vm and repeat the process of step 2 until all the n vertices have been selected and connected by n-1 edges. These n-1 edges constitute the minimal spanning tree. We will see how it works, how this Prim's algorithm works for a given graph G. Okay, here we have a graph with 6 vertices, which are the vertices V1, V2, V3, V4, V5 and V6. And this V1 is connected to V2, V3, V4, V5 and V6. V2 is connected to V1, V3 and V6. V3 is connected to V1, V2, V4, V6. V4 is connected to V1, V6, V3 and V5. Similarly, V5 is connected to V6 and V1 and V6 is connected to V1, V2, V2, V3, V4, V5. Okay. Now we are going to first write down the tabular form. That is V1, V2, V3, V4, V5, V6. Here also that is 6 by 6 tabular form. And these entries have been marked like this. V1 to V1 is nothing there. And V1 is connected to V2 with an edge of weight 10 here. Right? So that entry 10 comes here. And V1 is connected to V3 with an edge of weight 16 here. And so it is connected with 16. V1 to V4, it is connected with an edge of weight 14. So it is 14 here. And V1, V5 is 10 here. So putting 10 here. And V1, V6 is 17. Same way. Okay, V2 is connected to V1. As we are here, when we are going to consider this graph, when we are going to find the minimal spanning trees and all, we will be discarding. Even if the given graph has multiple edges and loops, it will be discarded. And we are just considering about the graph. We want to find a minimal subgraph with connecting all the vertices of a given graph. So now we will be always considering this symbol graphs. Okay. And V2 and V1, there is only one wedge between that. V1, V2 is the same with V2, V1, right? So we will be putting the same thing here, 10. V2 with V itself, nothing. V2 with V3, it is an edge with 9.5. V2 with V4, there exists no edge. So that we put this in front of V2 with V4 and V2 with V5. V2 with V6, we have an edge with power weight 19.5. The same thing happens continuously with these vertices. V3, V4, V5 and V6. Now we can see that it is a symmetric matrix with about the diagonal, right? 10, 16, 14, 10, 17. Here also 10, 16, 14, 17. 10, 16, 14, 10 and 17. Same thing. It is a symmetric matrix. Now according to the second step, we are starting from this vertex V1 and go through this row of V1. Now I have considering this row, I have two entries with least quantities, 10 here happening with V2 and here happening with V5. So I can draw either the lines V1, V2 or V1, V5. Just I am drawing this V1, V5. Okay. You can draw even V1, V2 and continue the process. V1, V5. And now I am going to examine the rows V1 and V5. And which quantity has the least entry is occurring in this 8, which corresponds to V4. So I am just taking connect V4 and just taking it corresponds to V4 and connecting V4 and V5. Okay. So on the next level, I can use this V4 and this entry which is 7, V4. This V4 level, this entry is 7. It corresponds either to V3 or V6. V4, V3 or V4, V6. Okay. Here I am considering V4, V6. Then again going to this V6 level and V4 level, I am going to this V3. Because V4, V3 is less weight when compared to V3, V6. And similarly, I am finding V3, V2. The resultant spanning tree is like this. Okay. This is the resultant minimal spanning tree of the given graph G. Here, the given graph G is here. First, then I found this and with 6 vertices, I found this 6 by 6 tabular form, and this entered the entries and just going to this, and this found this minimal spanning tree of this given graph. So in this session, we have discussed what is a spanning tree of a given graph, minimal spanning tree of a given graph and its applications, and we used Kruskal's algorithm and Prim's algorithm to find the minimal spanning tree of a given graph. Okay. I hope you all remember what are the things that we have discussed here. And Prim's algorithm and Kruskal's algorithm is somewhat easy when compared to Prim's algorithm in finding the minimal spanning tree of a given graph, given connected graph, which is weighted also. Okay. I hope you all enjoyed this session, and thank you for watching this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.